In this work, we propose a new method called SLANG to speed up Bayesian deep learning. In Bayesian deep learning, our goal is to compute a posterior distribution over neural network weights. This is different from deep learning where we only compute point estimates. Such a posterior distribution can be used, for example, to estimate the confidence of the prediction of a deep network. While this is very useful, the issue is that computing distribution is challenging. This is because the Bayes rule requires averaging over all possible neural networks, which is infeasible when your neural network contains a million parameters. So in this work, we propose a new method to quickly compute a Gaussian approximation by using variational inference. Now, many existing variational methods use Gaussians with diagonal approximation, which leads to poor performance. For example, see figure in our paper. So we propose a method to estimate a structured covariance approximation that uses a low rank plus diagonal approximation. Our work builds upon an existing work on natural gradient descent for variational inference. This existing work proposes a method called variational ADAM, which is pretty much like ADAM, but computes a Gaussian approximation to the posterior. The issue with this method is that it uses a diagonal covariance matrix. We extend this method by estimating a structured covariance that has a low rank plus diagonal structure. To keep the simplicity of the variational ADAM method, we refine our current covariance estimate only by using the back-propagated gradients. Basically, we use outer product of the gradients as an approximation to the Hessian, which is now fed to compute the new estimate of the covariance. This approximation is known as the Gauss-Newton or empirical Fisher approximation. Well, with this, we avoid computation of the second-order information using the reparameterization trick, and we simplify computation. Putting this Hessian approximation together with our previous estimate, we obtain the new covariance estimate by using an eigenvalue decomposition. We also refine the diagonal of the covariance matrix so that our method always performs better than the variational ADAM method. Well, due to the low rank structure, each step of our algorithm can be executed quickly, which results in a simple algorithm whose computation and memory are both linear in the number of weights in the neural network. Our results on logistic regression and Bayesian neural network show that our method not only converges faster than mean field methods, but also give better results than them. Our method compares competitive to the Bayesian dropout method. Overall, this work shows that we can speed up computations in Bayesian deep learning while using structured covariance approximation. Thanks for listening.